everyone to Pyohio. I'd like to introduce Alec Delaney. He's going to talk a little bit about himself. And he is here to do Python for hardware folks.
Morning, everyone. Anyone's first Pyohio? Yeah, all right. Cool. Welcome. Let's get started. So a little bit about me. I'm Alec Delaney. I am a senior hardware test engineer at Bevy, and early shout out to them for letting me take some pictures and talk about some of the stuff we're going to today with examples. My background is actually in mechanical engineering. I am also a part-time student in a computer engineering program. I'm a cyclist and a runner. I'm not particularly good at either, but I own the shoes, so it makes the list. I'm a parallel port fanboy. I feel like I missed something beautiful, and I'm waiting for the comeback. And I'm an open source enthusiast. And if you're interested in any of those things or talking to me about any of those things, the slides will have my Mastodon link below in the corner there. So for the sake of this conversation, let's scope in and say who are hardware folks, right? Kind of broad. I assume most of us are maybe some more software. So when we say hardware, who are we talking about? Well, I'd say hardware folks are anyone who designs, develops, tests, manufactures, maintains, makes or maintains, right? Any sort of hardware, right? So it could be PCBs, it could be fixing PCBs. I even have a 3D printed little jig there. At any point, if you touched any number of these things, or things not even on this screen that are in the real world, I think that makes you a hardware person. So pretty broad. And yet it's still really tempting to think that software and hardware are like completely two different categories, right? There's some overlap, we can all admit that, but you probably have two different teams, right? You've got your software people, they are mostly working on the computer, right? Maybe what they're doing, it's data that is represented in the real world, but their work is mostly on the computer. That's where the gold is. And then you got your hardware folks. They're, maybe mechanical engineers, electrical technicians. They use a computer, right, as a means to get by. But most of what they're doing is in the real world, right? They're making something, or that's the end product. And it's tempting to think that they're two different teams. Maybe they collaborate, sure. But there's actually a whole wide set of industries, fields, passions in the intersection, right? There are plenty of software people here that probably work on hardware. And it's not so hard to imagine that you have hardware people who are going to write software. So why would they, right? What are the reasons that these people that are mostly working in the real world would touch code in any capacity? Well, non-exhaustive list, but one, creating fixtures for making or testing parts, right? Maybe you've got an assembly line, and there's some complicated step that you need to do, and so you're going to build a test fixture for making that, or maybe checking it before it moves on to the next step. Maybe you're doing some data acquisition, right? You want to collect some data on some machine, some part, and you want to have that for later. Or maybe you're doing industrial automation, right? You're in a factory floor and you're trying to make an assembly line that can make, thousands of something. So maybe you're going to use PLC or something. We'll talk about some of these as we go on. So let's get started. What about that first one, right? Fixtures. Right? So fixtures, for clarity, are these small custom rigs for making or testing parts, right? Maybe it's a little, box-sized thing. There's no size requirement, but basically something that you are going to have in an assembly line or in a test process that's going to help you do some job, right? It simplifies and automates the process, right? Maybe it's hard to do by hand. Maybe you don't want someone doing it by hand. It's going to improve the reliability and the repeatability, right? If I were to measure something with a ruler, I'd say it's about an inch, right? And that works for a lot of things, but sometimes you're going to need more precision, and you're going to need it to be repeatable. So maybe you're going to use a test fixture for that. Sometimes you have parts that are really, really complicated, right? A ruler's not going to cut it. You're going to need something way more specific and way more complicated for your complicated part. Complicated parts require complicated tools. And sometimes the thing you need to test or make that part doesn't exist, right? Sometimes a ruler, calipers, whatever it is, it's not going to do that measurement, and you're going to need to go make it yourself, right? In those cases, you're going to have to build your own tools. You can see an example of one, not my test fixture, but if I remember correctly, this is a test fixture for a laser head reader, I believe. So they can be quite complex and quite big, right? They don't have to be palm-sized. This is great for microcontrollers, right? Making something custom hardware from the ground up, yeah, let's put a microcontroller in there, right? And for anyone familiar with microcontrollers, you might program those in C, or for the hip among you, you might be starting to use Rust. But what about Python, right? Could we use Python to do this? Well, sure we can. We could use MicroPython or CircuitPython even, right? So these are versions of Python that are made to run on microcontrollers, right? So whereas CPython is made for your computer, these versions of Python go onto your microcontroller, and then you can start writing code on top of that, right? They're essentially a specialized subset of CPython. So they have some things you might be familiar with, some things that are specific to the microcontroller, and once you have those things, you can start doing all of your embedded systems functionality, right? You can start doing all your I2C, you can start doing your reads, all these things to start building your test fixture or your fixture from the ground up and do all the functionality you need. So let's go through an example. Let's go through a CircuitPython example. So you can see here that I've got a microcontroller with an LED and a push button. Let's make something that when you push that button, it's going to turn that LED on. How do we go about doing that? So far, we're going to start with the microcontroller and import some things there. Some things might look familiar, right? We'll import our time module. We'll use that later. So you can see that we already have some things from CPython that we're used to working with. But we've got some new things there. So we have this board import, right? So this is a module that basically has all the information about this microcontroller. Which pins are there, what functionalities it has, what capabilities it can do. We'll import that and we'll use that later. And then since we're using digital inputs and outputs, we'll import this library, some things from this library, digital I/O. This is a library that basically contains all the things we need to start turning inputs, to read inputs, start turning things on and off. We'll pull some things there and we'll go through that list. So why don't we start with the LED, right? We'll take this object, digital in out, which is a class that represents anything that can be an input or an output. And inside of it, we'll feed it the information for what pin it's connected to. So we've connected that LED to the serial clock, the SCK pin, into that object, and we'll store it in this LED variable name. And since digital objects can be inputs or outputs, we'll just tell it that it's an output. So we'll set the direction property to output. Next, we'll deal with that switch. We will, again, use the digital in-out object. We will feed it its input, which in this case is D2. And because it's an output, we'll just tell it, hey, it's an input. We will feed it that it is an input as to its direction property. And as a little quirk of how embedded works, when we press that switch, it's going to connect it to ground. So we just want to make sure that when it's not that, it's not floating. So we'll use what's called a pull-up resistor, right? So normally it'll see high voltage, and when we push that button, it'll go down. No floating inputs, just one of the two states. So what we'll do is we'll set the pull property to be a pull-up resistor. And that's internal to the microcontroller. We're now ready to run our main event loop, so we'll stick that in a while true so it runs forever. And we will set the value of the LED actually to the opposite of the switch, right? So when you push the switch, it connects it to ground, so you'll see false. So we actually want to turn the LED on or true, right? So we're basically doing the inverted state. So we'll set the value of that LED to the opposite value of that switch, and then we will run time sleep as a debouncing mechanic, right? Switches, when you press them, they sometimes are in between two states, or they really quickly flip between those two. So we'll just use a little bit of a wait to make sure we can do that. And that's it. Now you press this button, and your LED turns on. And that's well and good, but fairly simple, right? Hard to imagine we could maybe make parts with this. So what would it look like if we were to build an actual fixture with CircuitPython? Well, here's one I built at Bevy. This is a fixture that we put in basically our marketing van that drives around with all of our machines. What'll happen is Bevy makes smart water dispensers, and so normally you find those in your office. But in this van, they drive around, and what we call this ice bank, which is what we use to cool our water, can slosh and spill around everywhere. So for the marketing van, what we did is we built a fixture that basically pumps all that water out, puts it in a reservoir. They can drive the van around, and then when they park, they can use this in reverse, and they can, might go. That's okay. When they park the van, they can use the fixture in reverse, pump the water back in. It's still cold. They don't have to wait for everything to cool down, which can take quite some time. So you can see they're kind of going from left to right. Up in the top there, you can see a pump and the power supply. Kind of below that, you can see some solenoid valves that we use to choose which which machine we are pumping to or from. You can see in the middle there's some water, some connectivity sensors in there, right? And we know we've filled enough water when those two metal bars connect. It shorts two pins, that's how we know. In there, in that black box, you can kind of see all of the other associated electronics, some relays, the motor driver for the pump, and kind of in the center there, you can see our microcontroller. So yeah, this is actually what we're using for out in the wild, right? This is great if you want to have something that is, throw some sensors on there, maybe you want to throw, again, a motor, whatnot, but what if we just want to collect data, right? Well, this is kind of annoying to have to build something every time you want to collect data. That's annoying. What can we do? Well, we can actually just use data acquisition, right? So what is data acquisition systems? These are systems that are used to just do that, collect data of a whole variety of types. So data is data, but why do hardware folks want to collect data, right? Well, first of all, our modeling only predicts so much, right? Our theories are only as good as our theories can be, and the real world is messy, right? Oftentimes we can't predict everything that's going to go into a product or the environment you'll find it in. Similarly, when we are building products, right, hardware people, like, it gets very expensive the further you go, and sometimes if anyone's worked with plastics or anything like that, molds can be quite expensive, right? And nobody wants to purchase a mold for parts and then find out that it's wrong. So we typically build prototypes, and it helps to build confidence in those prototypes. So we will do testing on those and make sure that they work, and then, once we have confidence in those, we'll go on to the next step. And then when we do that, right, maybe we find something that's wrong, or we want to look back at that data, right? Maybe we want to do analysis later, or we just need to reference that data, right? So collecting that data for later use is critical in those scenarios. So DAC systems are exactly this, right? They're general. They basically collect essentially voltages or currents, but that can be a number of things, right? It could be a temperature, it could be an input, it could be a whole wide range of physical things translated into those signals. What's cool about them is that they're configurable, right? Your DAC system can take typically any number of these inputs, and you can even configure, how often you're collecting them, like clock speed, things like that. So general and configurable, an excellent choice for this kind of use case. And if anyone's familiar, maybe you've used something like MATLAB to program these, or LabVIEW, which is a graphical programming language. Typically, that's kind of where you might be when you're using DAC systems, or maybe some other, more specialized language or not IDE, but platform. But what if we wanted to use Python? Is there Python for DAC systems? Well, yeah, there are actually instances of Python in this use case. Let's take the NI DAC-MX driver, right? So this is National Instruments. They make a lot of DAC systems. This is their driver for their DAC systems. And it does a number of things, right? First, it provides access for their own tooling. It does provide, for example, a graphical programming interface that's a little bit different from LabVIEW. But what it also does is it exposes an API that other systems, the other languages systems can use. And where there's an API, there's usually Python close to follow. And sure enough, there is a Python library actually supported by National Instruments, creatively called NI-DAC-MX. This is a great library that if you're writing in Python, you can just connect to one of their systems and start writing code, and you start getting that data, you can save it, you can do all the normal things you typically do in all those other programming languages. So what would that look like? Let's walk through an example here again. We'll start by, as always, importing a couple of things. We'll import that NI-DAC-MX library. That's basically our main interface for how we're going to work with this. We'll also import some constants from that library. Acquisition type, basically telling it, hey, this is the kind of acquisition I want you to do. That's probably the most important thing there. And then,
just because we need something to show, why don't we import matplotlib, right? So we can have some cool things to show here, right? We can show all of our other team members, hey, look at this data, rather than just showing them CSV. So we'll start with these things called tasks. So tasks are basically how NIDAC MX works. A task is basically anything, any read, any output, anything like that. We're going to call that a task. And when a task is ready, we're going to send it off to the DAC to perform. So we can do any number of tasks. We can have any number of things in that task. So for simplicity, why don't we just start with an analog input, an AI voltage. So we're going to read some voltage from that DAC. We're actually going to read from the DAC that's named dev1, and it's the first channel, which is 0 index, so we'll read from dev1/AI0. That is the basically address we're going to use, and we will add that to the task as one of the AI channels we're going to be working with. We're also going to do a couple other things here, right? We can configure that read to do a couple of things. We'll do some things with the clock timing. The main one we want to look at here is that last line there, the samples per channel. This basically says how many samples this channel is going to collect as part of this read. We'll set it to 50 here, right? So when we do this task, we are going to collect 50 data points at that specific clock speed. And so we can go ahead and do that, right? We'll take this task, we'll do a read on it, right? We'll tell it, hey, I want you to read all available channels. And we will store that in creatively named data variable, all the results from that. And then because we want to show our results, we will plot that. So we'll plot that data because we are good data scientists. We are going to label our y-axis, not our x. We still have room to improve. That's okay. We'll label that graph and we'll show it. And so you get maybe something like this, right? And so now you've got your data, you can do everything else you want, right? You can save this graph, you can store that data, all of the things you might want to do. And that's all well and good, it's maybe not super impressive, but what if we wanted to use this for something a little bit more complex? Well, here's an example. This is a picture of Betty's lab. You can see us testing all of our smart water dispensers here. The main thing to note here is that what we're testing is these things called pressure switches. They're like pressure transducers, except instead of telling you what pressure you are seeing, they just tell you whether you're above or below, right? So they'll be on if they're above a certain pressure, and they'll be off if they're below. And we use these in some of our machines to figure out, when our CO2 tank is, needs to be replaced. We can actually see those there. We're testing a couple different ones that are connected to the CO2 tank. And if you follow the spaghetti wire up to the DAC there, it is sitting on that table. This is a National Instruments USB DAC. It's palm-sized, very wonderful, very versatile. And then you can actually see it go all the way back to this obnoxiously long USB cable back to the computer, right? So what I'm doing here is I'm basically turning the CO2 tank on and off and letting the pressure rise and bleed, and basically seeing with transducers as well connected when it actually does, right? So now we can actually test, like, hey, these pressure switches, we think they're turning on at this pressure, but how close are we, right? With pretty good precision too. And this is great for development, very easy to work with, but you can imagine that this would probably get very difficult if we wanted to do this on hundreds or thousands of these parts, right? What if we have a manufacturing line and we want to test these before we send them out, right? We want to make sure, hey, when we send the customer this, it's exactly within our specification. This is not going to cut it. We would need to use something more like industrial automation. So this is anything where you basically want to do this at scale. So why would we use that? Well, there are a couple of reasons, right? Again, scalability, right? Some things are just not going to be able to do by hand fast enough, so we're going to need to automate that process. Similarly, there are plenty of environments that don't play well with equipment, high voltages, corrosive environments. You're going to need something a little bit more rugged than maybe your USB DAC. Maybe we want to reduce part-to-part variation, right? Again, not just when you measure something, but when you make something, right? By hand, it could be, give or take a little something, and so maybe we want to automate that process to really rein that in. And similarly to the equipment, right? Sometimes our environment is not safe for people, right? Again, if the equipment can't handle corrosive environments, people are going to fare far much worse. So maybe we want to remove people from the equation for their own safety. You can actually see an example here of a very, very simple system. This is basically a water boiler, right? The way these work is you have a temperature sensor in there and a heater in there. When the temperature is below a certain temperature, the heaters will turn on, and you'll keep reading that until you see you're above temperature, and then your boiler turns off, right? So very, very simple, all right? And this is very easily controlled through what we would call PLC, a programmable logic controller, right? These are standardized ways of making automated systems, particularly in things like factories, right? Any kind of industrial automation where you want automation, PLCs are a pretty good way to do that. Because they're standardized, they're not only standardized in how you work with them, but they're also standardized for the environments they'll see, right? So no need to build your test fixture to be able to handle these environments, right? And then pray your microcontroller doesn't get fried. PLCs are built and standardized to handle these kinds of environments. So if we want to use Python here, what could we do, right? The normal ways you program these are through maybe something like CodeSys or some other more specific languages. So if we wanted to do Python, it's hard to imagine maybe, the way we code these things is standardized, how we might do that with Python. But there actually is, there are some out there in the wild. I have not used it, but as a case study, let's look at the Revolution Pi. This is a programmable logic controller based on the Raspberry Pi. It's actually the compute module in there. So you have the power of the Raspberry Pi, but built around it is the ruggedness shell and all the other things that you would expect from a PLC. This can run things like ladder logic, which is how you might typically work with PLCs. But you can also run Python in the background, right? While Python can do your control logic, a great example of where you might use it here is for doing things in the background that are more complex. The ladder logic can't really handle, right? Maybe you have a database you want to reference, right? You can imagine that ladder logic, which is basically telling circuits when they should open or close, right? Very hard to tell it like, hey, just connect to this database. It's not really going to cut it. What you can do is you can have all of your control logic in this very specific PLC language or one variant of it, and then you can use Python for connecting to databases, right? It'd be way easier to just use the request library or some third-party library. So that's how we would do that. So clearly there's ways of doing things in Python with all of these, PLCs and microcontrollers, but those are kind of the exceptions, right? Why aren't these more common, right? Why are we talking about Python as the exception and not the norm here? So to answer that question, first my own, does anyone know what this is by a show of hands? That's okay. So this is actually a geometric dimensioning and tolerancing symbol, a GD&T symbol. So this is what you might find on an engineering print that basically tells you, hey, this feature we're making needs to be tolerance to this degree, and if it's not, the part isn't correct, right? If it doesn't fall within these specifications, the part's not going to work, right? It's not going to fit. It's going to break. It's going to do something, right? So it's telling you how well the part can actually be made. And it's not a terribly complicated system, right? You can see there's only 5 components shown here, and it's tempting to think that if we went through and we explored this one and maybe some others, you'd start to get a feel for it, right? You'd start to understand, hey, this is tolerancing. For reference, I took a 3-day class, so it's, you can learn this kind of thing, and you start to build confidence and know these symbols and maybe how to read a print. By a show of hands, who thinks they could make this part after 3 days of GD&T? And it's in German, and that's not what I'm talking about. Yeah, this is a part. You can see some GD&T symbols. Maybe some things look familiar, right? Maybe we see some lengths that we need to make, right? With maybe some tolerances, maybe some diameters. But there's probably some symbols on here that we haven't talked about that are a little confusing. This is what Python can look like to hardware folks, right? Some things are familiar, you kind of get it, maybe you get the gist of what's happening, but if you wanted to go make this part, right, go build that code, or read that code, very difficult, even if you know a lot of the basics. So what are the barriers, right? If this is what it looks like, how can we change this? Why is it like this way? A handful of reasons. First of all, skill sets are different, right? Hardware people do have different passions, different backgrounds, they have different prior knowledge, right? So getting them It's not like they may not know another programming language. So learning Python, they might not have anything prior to pull from. Similarly, they just don't use the same tools, right? They don't know, they may not know what Git is, and they may not even know how to use a command line, right? That's not what their skill set is. They have no idea how to do that. This is to say nothing about setting down environments. I'm not even talking about Python environments. Just their whole computer in general, right? They may not know what a package manager is. And all of this being said, right, that's a huge investment cost, right? That's a huge amount of time to invest in something just to build maybe one fixture, right? Maybe it's a special case. So if these are the barriers, how could we overcome them? So this is, again, a non-exhaustive list, but here are some solutions I propose, right? I'd say first, become a mentor, right? We're the software people. I think it's on us to really teach hardware folks how to use Python, and at the same time, we should learn from them, right? It's going to be a journey to teach them what an object is, but I think that there's a lot we can do once we teach them those basic building blocks, and that we can learn from them as well, right? Maybe we can learn what they're doing and what a GDT symbol is. Also, collaborate on projects, right? Again, if we're the experts on software, it's a little bit on us to make sure that we can work with them on these things. I would say for these projects, start small, right? You don't have to build your whole factory automation in Python from day one, right? Start with a simple fixture. Start with a simple rig, right? The pressure sensor thing I showed was only a handful of lines of code, really. It's not much, but it did its job. Start there, start small. Addressing some of the more technical points, I would say start with graphical options, right? Hardware folks don't really, they may not be familiar with the command line, and there are tools out there that are better fits for them, right? I would propose as an example, GitHub Desktop, right? Using GitHub Desktop allows you to use Git and GitHub graphically, and this is going to be huge, right? Getting your hardware person to start using version control is going to be massive, right? They'll start being able to make reproducible builds, they'll start being able to get reproducible builds, and you'll really see a huge efficiency boost there. The more you can steer them to what they're familiar with, which is graphical options, the better it's going to be. Similarly, I would recommend steering them clear away from anything complicated in terms of environment management. I would suggest something that can very quickly and simply build reproducible environments. Take Conda, for example. Getting them to use something like Conda to manage their environment is going to be way easier than them mucking around on the terminal trying to do it themselves. So again, get them to use existing good tools. And on some level, right, this one's really entirely on us. It's a little on us to learn and contribute to these specialty Python environments, languages, platforms for hardware, right? All of these things that I've talked about are open source, right? CircuitPython, MicroPython, even National Instruments' own library, all of these are open source. Go contribute, go learn, and pick up a hardware person and enjoy learning with them and teaching them. Before I finish, a big thank you to everyone who uses a Creative Commons license. Thank you for letting me use your work here. Thank you to Slides Cardboard for the presentation template. And yeah, if you're interested in this slide deck, you can see the slide. You can find the slides with this QR code. And please ask me questions. If you're at the conference, please feel free to pull me aside. Otherwise, my contact information is on screen. Please feel free to reach out to me about this or anything else. Thank you.